Okay, guys, so in the last calibration attempt, we established that the thermocouples fell apart. Um, and they looked like they were falling apart a little below 1,000 degrees centigrade. And it turns out from doing a bit of research that these thermocouples are good from 0 to 1,000 degrees centigrade, but not really suitable for long-term use above 800 degrees centigrade. So they can detect up to 1,000 degrees centigrade for short terms between 800 and 1,000 degrees centigrade, but you don't want to be running them in a hot tube like we were doing because they oxidize and then fail, and you get thermal drift and all kinds of problems which we saw. Of course, we don't want those kind of things going on because they would look like excess heat. And in fact, Lion did send a thermocouple and go, "What's going on here?" Well, basically, it epically failed, like has been established. And we look to see that there are ceramic thermocouples which we can get, which do not fail in this way, and we'll be able to use those for future more robust calibrations. But what that means is for this run, we're going to do something a little bit different to what we've been doing before. We know that from the previous run, at 675 degrees Dwyer temperature, the active internal temperature was 960 degrees centigrade. Okay, and what we're going to do is use the pulse width modulator here, which is currently set to 0, to manually achieve fixed active internal temperatures. So this is the active side over here, and then let that settle to a flat line, and then see what the PID controller over here is showing. So they will be our future set points that we're trying to achieve, and then we'll know that that should be achieving a certain amount of temperature in the active side. Okay. And what we've also done is we've adjusted the position of these thermocouples so they don't go quite so far in. So comparison to the active cell, we are now looking at something like this on the position. If I can try and let it stay there, maybe it's just going to roll away. But anyway, something like that. So the heating coil will be working on the fuel in the middle. And this means that the thermocouples aren't likely to touch any wires that might have come off the end of the fused quartz in there. So we should get reliable temperature from that aspect. And what we're intending to do is essentially go and try and get calibration steps from 400 degrees up to 900 degrees internal active temperatures in 100-degree steps by, as I said earlier, adjusting the PWM controller on here. And this is actually the kind of way that Lion originally worked. Of course, it's clear that he overstepped the capability of the thermocouples based on having one sent to me, which is in a terrible state. He did have them offset. Now, the good news is with our thermocouples behind the insulation, they never exceeded the operating temperatures of these thermocouples for long-term use. So once we've done this calibration, they should be good, although in future runs we might like to get a couple more new ones of these to apply, and maybe even choose the ceramic type, which will not fail in this way. Because the actual thermocouples themselves, they can read up to 1250 degrees C quite easily. It's just the sheath is failing and causing all kinds of problems, as we have seen. Okay, so that's what we're going to do. And so I'm going to ask my friend and colleague here to fire away. And yeah. What are we doing? What are you doing? You're setting the Dwyer to try and achieve 1,000 degrees, which it's going to fail to do because it's restricted by the PWM here. And we're going to manually try and target temperatures of first 400. So we're going to have a bit of up and down, and that's going to give us our set points. Having a rather nice crisp apple here. Yummy, yummy.
Wants to connect to the cloud, so I have to prevent that. Okay, set point is set.
675 is the set point. It's not going to achieve anything because we're not giving it any power at the moment.
Okay. Reading is still working. Good.
What spot is it? Getting hotter, by the way. So the PWD at 0 is actually still doing something because I can see the full amps on there at the moment. It's 100% on.
Yeah, we dialed it full back.
Yes.
But it's not really 0.
No, clearly not. But I can see, although it's saying 47, okay, I can see it's doing 0.053 kilowatts. So it's doing 53 watts in at the moment.
We should wait a bit to see where it settles.
See where it gets to. So this is the PWD set to essentially 0. Well, it's not 0, but it's got some on time. In theory. It's leveling off. It's leveling off.
The thermocouple is very fluctuating. I wonder if we.
Well, it's very. Oh, they're tracking nicely.
No, but that's way too much fluctuation. I should be very smooth at that point.
Mm-hmm.
Nothing changed them. Let's see now. All good. Jumping way too much.
But their voltage biases.
I can't see now because I'm connected.
Well, disconnect. We're okay for a while.
Okay.
Just check. It just disconnecting from the thermocouples. You can see the temperature rising based on the options at the moment. We're going into the control software for the LabJack T7 Pro, where we can set the thermocouple parameters. I can see that's minus 0.01 volt. Should be 0.1. That should all be 0.1. No, but down there, aim 6.
We don't use that.
Okay, all right.
Just here.
Yeah, okay. Okay.
0.1, aim 2, 0.1, and 4. Also, just this one is
That's
the
wrong.
lower settings, but that is room temperature.
It's still wrong though. Should change that.
It's good up to 250.
Still change it. It should be.
Looks good.
Okay.
Oh,
Might be.
just
Yeah. It might be that it's because of the PWM. Because it's acting like a magnetic core, and it's chopping the signal,
Mhm. Yeah.
and you're seeing noise.
Right. That could be. We didn't do that.
We didn't do
before.
it. We've had it fully on, haven't we? So it's either on or off.
Yes.
So you're already seeing influence of the
Mhm.
electromagnetics in the core, even without the secondary coil.
Yeah. that
But
could be.
it's giving us a kind of an approximation.
So
It's punching the power on and off, punching it on and off, isn't it?
Yeah.
And you're getting a mismatch between the sampling when the power's there and when it's not.
Mhm.
So it's going to be noisy because we're putting noise on it. I should get the ultrasonic mic and listen to it.
Oh, yeah. Mm.
Settling off. It looks like it might be. It certainly is on the Optrus. It looks like it's flattening out.
Yeah.
Yeah, you can see.
Mhm.
This is the yeah.
Yeah. Goes down. Stabilizes soon, I guess.
Yeah, I need to.
Mhm. And these fluctuations should change when we dial because
Yeah, because the pulsing addition is going to be less choppy because it's going on, off,
Mhm.
on, off, and later it's going to be going on, off, on, off, on, off. Hello, Chibi. G'day. It's myself here in Artifact, and keep your wings. So this is going to be a manual control. And if you weren't with us a little while ago, we have discovered that these thermocouples obviously failed in the last run. And when we pulled them out, they looked like they had failed.
Yep.
And so we went into the spec sheets and we found that they're only good for 1,000 degrees for short bursts. Really, for long-term use in an oxidizing environment, forget about it. Above 800 degrees C. So we are going to use the pulse width modulator here to vary the input power. This is the PID is already set to 675, and at 675 it was already seeing 960 in the active internal in the last run. And so we're going to manually try and set points where the active internal temperature is reading 400, 5, 6, 7, 8, 900, and then see what the Dwyer is reading for those, and those become our set points for experimental runs. So Ron Sykes, thank you. Essentially, what's happening here is because of the pulse width modulator, it's a bit noisy on the signal from the thermocouples in the cores. But you can see the temperatures are a little bit more predictable when you see the 10-second averages that the Optris is doing here. In fact, if you look at the Optris, you can actually see where we now have the screw threads coming out of the core, placing the tip of the reactor cores in a more optimum position for heating during an active run. Still some separation there, but we always have separation. So it's okay, it's expected.
Should you think something?
So where is this trending to? Looks like it's trending somewhere to around about 130 degrees, I would say. So I think probably, since we don't care about this temperature point, unless we do, we want this as the low temperature, do we? Or should we leave it till the flatten out?
I would, yeah.
And then we have a low temperature point. So whatever this is going to be a low point. But of course, we don't know. Yeah.
So maybe if we just want to bake something, we know what temperature this goes.
Yeah. I mean, we can already see that the Dwyer is reading. The Dwyer reading 47 degrees. And it's actually tending towards maybe 140 in fact. It's summer here in East Germany. Not in the cellar though. It's still very much winter, autumn temperatures.
Oh, not that bad.
Autumn then, or spring.
Nearly 19.
Early spring. Yeah, which is good.
I think when we started, it was 16.
Yeah.
But I heated from 14 up.
Aha. Okay. Room temperature that you can see down there is reporting 18 degrees, but it feels a little bit cooler than that.
It's 19.
Okay, yeah. Near the reactor, but
No. Should be at the wall behind it.
even 40. So your Dwyer has to be set to about 30 degrees for it to actually be over 100 degrees in the core.
Yeah.
No wonder when we baked our dummies,
Oh yeah.
they were a little bit surprised. Oh dear. Um, On site says it's the first day above zero there in Alberta, Canada.
Wow.
4 foot of snow outside.
Well done.
Yes. It's for the people like you that we think most of when we're trying to look for heat on these processes. How was the experiment going, Bob? Says JDP2571. Well, we've learned a lot, let's put it like that, about calibration. And this experiment is not trivial in terms of being sure what the temperatures are in the core relative to the control that you're using to manipulate the temperatures. Right, last fact.
Yeah.
And so over the last couple of days, we've done several setups, and the last one we learned that the thermocouples are able to get fritzed by being over 800 degrees for extended periods of time. Paul Harris says, "Hi guys, sunny and warm here in interior British Columbia. Welcome to the show." So yes, our previous attempts with the thermocouples, I have a photo which I can show you for your viewing pleasure. They ended up looking like this. I will go in front of the high resolution camera over here. So it ended up looking. Let me try and get this so it doesn't rotate on me. Okay, here we go. This is what the previous thermocouples ended up looking like.
Yeah.
Not good. Not good way. There. Look at that. So we are doing a manual adjustment of the pulse width modulator with the Dwyer PID set to 675, which was the temperature at which it already exceeded 960 in the core, the active side. And so we will be doing manual steps on this. And the first step is with the PWM at its minimum setting. And so you can already see that that is achieving 153 or so degrees, 156, something like that. It's a bit noisy because, of course, the PWM is turning on and off. And so when the lab jack is detecting the temperature, it's one or more of those times when it's closer or further away from the being turned on or off. As we increase the duty cycle on here, the noise in there will get less.
And I thought something was wrong.
Are you looking for transmutation? Definitely not in this particular state of the experiment. In fact, it's unlikely we might even be able to do an active run in this kind of weekend, and it might have to shift. And that's okay, because we found out that the fuel discs that we have were not fully prepared by the late Neil Creighton-Gould, and that we have to prepare them, and that takes it's a 5-week process. So we have to. This is very useful what we're doing here right now, because around this temperature, like we're at 156 degrees centigrade. This is almost the temperature that we need the thing to be running at to bake the nickel discs. So this is actually quite useful what we're doing right here, right now, because they need to be baked at 200 degrees for a week and then chucked in the heavy water for a month, right? So we're actually getting to understand that if we have a little tube like this filled with the discs, like this, filled with the little discs, and sat in there, this is kind of the operating temperature we need to run it at. I need the adapter and the phone for that. Ultimately, we'd look for transmutation, but definitely not in this run. More, what we're looking for is signs of strange radiation. And when we do an active run, which will, as I say, probably not be this weekend, we will use these Echo Film 30 temps films, as was actually pioneered by the late Neil Creighton-Gould. And we will take the core, the so-called active core, and place it in a tin with 4 of those, and see if we can see these double spots or other X-ray structures being synthesized. Okay, for those that are just joining us and didn't see any of the other control runs, this is a LabJack setup that was built by Ryan Hunt, and this was used for the basis of the Me 356 Thomas Jezierdenek Aura experiments. The power analyzer here, the PCE 830, is reading current here and voltage. That gives us our current watts with the amount of the pulse width modulation going on, and you can see the total watt hours here. And this, along with this Optris PI 160, which you see here, was used for the verification of the claims of the Lugano report of Andrea Rossi. This device here, and a good proportion of the equipment here, was built and configured by the late Alan Smith. This was an innovation here, along with the PID controller, by my friend and colleague Alan Goldwater. And the software that you're seeing in the bottom right-hand corner of the screen is by my colleague and friend here, Artifact, who's in the room with me, but he's quiet. Oh yeah, this actually is quite close. This might actually get up to the temperature at which you need to bake.
Yeah.
So this is actually a very useful bit of data.
But I don't know if it's useful to have the heat be spiking like on off instead of.
Well, it's gonna get thermal equilibrium, and then it's gonna be smoother. The actual heat's gonna be smoother. Because you achieve the heat loss compared to the thing, so that the input heat is less significant with each pulse compared to the heat that's already in the hysteresis sort of situation that's going on. So you can that's why this is like coming down, because Also, you can also set the temperature here to 200.
No.
Well, no.
Yeah,
well,
both.
Yeah.
Yes.
but we will know that it doesn't need to be 200.
Mhm.
You can set it to maybe 65 degrees C here.
Mm.
And then this will be turning that on and off to maintain. Yeah.
So,
Yeah.
just checking if it works. 53, 54.
Oh, very good. So we have the two center points here, these areas here. They are 10 by 10 pixels above where the cores are aligned on the top of the little robot. And they are averaging over, I think it's 120 samples, the average of those 100 pixels to give you the two active and control areas here, which you can see are within about a degree of each other for those areas. Using an emissivity of 0.95, which is the emissivity recommendation in the Optris manual for ceramic. And we found that during our testing for the Lograno report verification that actually that was the setting that worked quite nicely to match the temperature assessed by contact thermocouples of two types and also a dual beam Williamson IR spectrometer, thermal bolometer type device. Pyrometer, rather, I should say, is the correct word. Okay, so I think it's going to get to 200. It's not far off, is it?
To 200?
Yeah, it's not far off 200. Like it's trending up, it's flattening out, but it's going to take quite a while to flatten.
Yeah, it might take a longer time.
Yeah, it's still got a fair rake on this curve here when you look at it like that. That's because it's got to get this whole thing thermal equilibrium. Honestly, it might reach 200, but it might take another 2 hours.
Yeah.
So, what do you want to do?
Yeah, I think we shouldn't wait too long
No,
at this point.
I think the baking thing is something that you can learn over time to do.
We will have to wait anyway when we go to higher temperatures.
Yes. So, what do you want to do? I think maybe we'll go for that first step, 400.
Or maybe it's easier if we go back and wait at the at zero input, zero, and to reach equilibrium in the cooling phase later.
Oh, I see what you mean. Yeah. So the thing is, do we want 1, 2, 3, or 1? Let's hit the 400. Yeah, attempt to hit 400. Of course, we have no idea what it's going to be, so it's a suck it and see. Something around 400 we're going to be targeting, and this is going to be manual. So we're going to be dialing this a little bit, and this is the PWM. We'll see what happens.
We should have a cardboard and mark.
Well, only when we know where we are. Yeah.
Just
so the reason we're doing this is that we need to set the specific temperatures achieved in the active internal, and that will tell us from the Dwyer data that you can see here, this active Dwyer data. We will know the temperature that we need to set the Dwyer to achieve the active internal temperature. Not that it's set to try and get to that temperature right now. Okay, that's clear for everyone. What? Before I dial in.
I think like a quarter or a third.
A quarter. And it goes round to about there. So it's not a full turn, is it? So quarter. Let's dial it to there. Here we go. Something's going to happen. Or nothing.
Yeah.
No, here we go. We've got to change.
in a bit.
Not overly impressed with the way that changed.
And it's doing something.
Well, we can see here on the sample over a second the amount of, what is it, a second or 2 seconds? The pole rate is averaging
This one is which one?
the PCE 830.
For the duck, it's 2 seconds.
Right, so it might be sampling internally at a very high rate because it does
Mhm.
the 50th harmonic. It must be sampling at a
Yeah,
phenomenal
right.
rate. But it's only giving a reading every 2 seconds. So we can now see that it's putting in 0.7, well, 75 watts. So what I'm saying is here that over a 2 second averaging, even with the pulse width modulation, the power and harmonic analyzer is assessing that there's 75 watts going here at the moment.
Yeah, it's going.
Yeah. This one needs to be. There we go. You can see the power.
Mhm.
It's looking at this point here, the hot point. You can really see a change there,
Yeah.
whereas everything else has got thermal mass to move. Much clearer on that signal that something happened. And I can already see that it's tailing off. So at the rate of curve, what do we estimate that's going to hit? I don't think it's going to hit 400, is it? It looks like it's going to hit maybe 300. So because the rate of curve
Mhm.
here compared to the rate of curve here, it's actually going to fall off quicker, isn't it?
Yeah. Mhm. Maybe 250 or something.
So we want to crank it a little bit more.
Oh, that was very little bit.
Well, trying to be conservative here. So we should see another little kick up. Yeah, there we go. So we found a use for the hotspot now.
Yeah.
The hotspot is at least our indicator that something's happening, which is relatively quick feedback.
So you cannot see the power steps on that.
Oh, that's nice, yes. So we can see now it's actually putting in 90 watts around. Wow. So this is where the power analyzer here, the PCA30, is really, really useful because we can actually say, and we can, finally, we can say what power input is what temperature in the core.
Yeah, because now it's running all the time, not
Yeah.
it's
Yeah.
not disturbed.
We actually have a power to temperature assessment because this is the 2 second accumulated power amount. Fine. I was having this whole debate with Artifact here that what Alan Goldwater did was he did a power input to temperature output, and that's kind of calibration you actually need to be able to have a understanding of whether it's producing excess heat in terms of how many thermal excess heat relative to the input power.
But for that, we need to use, well, if we want to have automation, we need the servo to.
Well, no, we don't. We don't know because when we see a certain temperature, we can back propagate it to the calibration curve which we're building now.
Yeah. Mm-hmm.
That's it. That is what we want. Finally. Good. Excellent. I'm happy about that. And it's pretty stable on the 90 watt point there. Of course, we do really have to let it settle at a thermal equilibrium. That means seeing it flatline, which means tedium. The only way you can get around that is to have automated, is to have a piece of software that sits there and says, this has achieved the same temperature for the last hour. I'm now going to give it another power step. This might be the longest one to achieve thermal equilibrium. So where do you estimate now the rate of it's going here? This might achieve 350, 375. No.
It's difficult to say because this was so short. But it will be enough. Maybe 300.
Might be quicker if you use a vacuum oven. Well, it's not just conditioning the nickel; it's conditioning the nickel and the diamonds. The idea is that you are degassing it. But that anyway, that was the protocol he used, like in air, 100, 200 degrees for a week. So if we're replicating it, we don't change anything. What we are finding out is that there are areas of possible failure and potential pseudo excess heat being thought about because of the type of thermocouples failing the sheaths. Really stable 89 watts there, isn't it? Input power, very stable 89 watts.
Oh, we're not changing anything.
No, it's good. For calibration steps, it's very good. It's actually much better using this because you get something that looks like a step rather than a lines, which is more lines.
Yeah.
You actually get some data rather than something you can make no sense of. You know, I didn't change the title on the video on the stream thing up there. It's, yeah, it's like manual. Oh, there we go. I guess is where I am. No, it is not your typical easy bake oven. Although it would be efficient, we only need to achieve 200 degrees for the baking process. And so yeah, you need about 70 watts, 65 watts or something.
But please, we are at.
I know we are now, but we're well over 200.
Oh,
I'm saying to achieve 200, probably only about 65 watts.
Mhm.
Of course, you could set up something quite simple. Firstly, you don't need to be heating both sides.
And you can insulate everything.
Yeah, but then you're going to have to recalibrate everything.
Just for baking.
If you mess it around,
Oh.
I mean, but you could get some of your Cantal wire and just make up a thing.
Yeah.
For the baking.
Yeah.
Have a thermocouple. You could maybe hook up the Dwyer and make a mini baking oven.
That was my plan for early diapet testings.
Right, yeah.
Just have a little small insulated thing and and a TC inside.
Yeah, done. Yeah, that makes sense, right? And also, you don't want to be abusing the little robot or something like that for a long period of time.
Is it updated?
Yeah, if it's zizzing over here, it's updating. what's going to happen is this is going to peel off to the left in a minute. I can change it, right? And that's the maximum, you can see. But like I can do this, which is, you know, hold, turn the hold on, and then this is the non-hold.
Doesn't look like I'm going much over 300.
Yeah, I mean, if I flatten this out, yeah, I think you're right. It's gonna trend to 250 maximum, maybe 240. So we need to crank it up a little bit more, don't we? So again, we're trying to target this 400 degrees. Yeah, it had a high pulse last night, but that pulse was the failure of the thermocouple, which we established very clearly today. Right, so what are we going to do here? Another 20 degrees?
At least. Go to 15 fast or so.
Let's see. Get our immediate response on our. We might be out of range in a minute on our
Oh, yeah.
hotspot.
Oh.
136 watts.
Getting.
Well, yeah, because it's far from where it wants to be. It's quite a big step we just did there.
So interesting later to see where how much noise is coming from which setting.
Mm.
And if there are noises at all, if we go full power.
Mm-hmm.
Probably not, because it's just a full.
Yeah. If it's just fully on, yeah. But I mean, it's the difference between the sampling regimes, because this software is averaging 121 samples, 120 samples to get its figure, whereas this software is taking it from the lab jack, which is taking an instantaneous sample once every hour.
Settings 25 milliseconds,
Yeah.
and then it gets averaged to a second.
Oh, right. Okay. Again, the power input is very stable on here, 135, 136 watts. And your software is recording that quite reliably here. Yeah, before what it was turning it on, and if it caught it whilst it was on, then it showed you the power. But sometimes it did a 2-second average with some of it on and some of it off, so you ended up with spikes that were lower.
Mm-hmm.
Whereas right now, within every 2 seconds, this is probably turning on and off in a fair number of times, and gives a fairly reliable power view. And yeah, Am I wanted?
No, not really.
Not really. Uh-oh. Oh, it's hit that. We need to change ranges now.
Mhm.
So what's happened is this is 0 to 250 degrees C, but the hotspot, which is our good indicator, is now clamped at 275 degrees C. So we need to change ranges here. So we get a configuration which you can't see, unfortunately, because it's only capturing a window. And we're going to change this from 0 to 250 to 150 to 900. Okay. So now our hotspot is back in the room and it has to change the parameters here. Okay. And I think at this point we are going to do a Ravi.
Mhm.
And
Okay, well,
yeah, because they're at the bottom of the range.
yeah.
So we have the opposite problem. It can't see what these active and control areas are because they're all, everything, even the background's at 150. All cooking. It's just the way the calibration ranges work on the Optrus. So it still looks like it's going to trend for about 350, doesn't it? 360,
Yeah.
370, I don't know. That one was never going to, the previous step was never going to get to 400 for sure. Maybe 290.
Mhm.
So I think this is going to go to about 370. I think we can crank it up a bit more.
Yeah.
So let's see if we can get our power to 150 watts. 143. 150. Don't breathe.
But wouldn't be a problem if we overshoot. We just have to dial back a bit.
Mm-hmm. We are the PID today.
Yeah.
Yeah. Yes, our robot wasn't giving us the right results. It didn't have enough intelligence. Maybe it does, and maybe it's our failure for not being able to know how to control it properly. However, whilst it's laborious, what we are doing will yield us actual data in several ways. The active Dwyer temperature that we need to reach in order to reach an internal active temperature, and the amount of watts that got us there.
Mhm.
In this case, it's gone. No, it was back up. As I said, for those joining us, this is all clamped at 150 degrees because of the temperature range we're on, which is 150 to 900. Really, we're just looking at the peak temperature here as a guide for what is going on in our experiment.
Now the hotspot is much lower than the max temperature.
Yeah, it looks like it's going to at least get to 400. So should we dial it back a bit? Take it down to 140
Which one are
watts?
we looking at? The yellow or the
Well, the active internal is the one that has our target, and currently that is looking like it's going to exceed 400.
Yeah.
So we're going to have to dial it back. Let's take it down to 140 watts. We were actually looking at hardware modules to convert 0 to 5 or 0 to 5, 10 volts to PWM yesterday as a different means of manipulating this electronically.
Yeah. One, two, one. Noisy. Very close.
Not far off, is it?
Six. I mean, a little bit.
No, tweak it. Maybe it is the 140 watt point.
Didn't change anything.
No, you wait. It's going to go down. It's not 141 watts now. It's going to go down. Just yeah. He says, "It's done." Maybe I'm caught between two steps. You know, I don't know what the resolution is, but I definitely moved it. Is it still going up? Isn't it? Okay, so
Okay. What's less?
it's still rising, isn't it? Now I know why they invented PIDs. I know it's going down. It's rising and going down at the same time. It's annoying. It's definitely still trending upwards, isn't it? 134 watts. 133. All those times I've criticised PID for overshooting, I take it all back. Still maintains unforgivable to continuously undershoot.
So
Looks like it might be going down or leveling.
yeah, the numbers may get higher, but it's fluctuating more.
Yeah. I know it's going down. It's my body temperature. I need to go and put a jump on. It's not exceeding 100, 420, is it? At all.
It's pretty flat now.
It's getting to be flat. I just want it to be flat a little bit lower. Come on, play ball. Well, what do you think? 130 watts?
Um,
129. It's a lovely number. There's only one number better than 129. It's 128, and there we go. Stuck between the two. Yeah, it's a shame we have that fan. Because if we were going to record any sound, that's going to be a large component of it. But it's okay. They'll still see the high frequency. It'll just be a very much lower decimal level. I have to say, is this fanless, this computer?
it has a fan, but it's
Barely uses it,
yeah.
right? Still stubbornly above 410, isn't it? Yeah, come on. 125.
I think it's going down.
You think it's
Just
going down?
slowly, but we don't need to go far. So if you go
Okay,
down
there we go.
half power, we'll have to go up again.
Yeah.
Again.
That's how it works. 124 watts. Hello, Joseph Fuller. Happy Easter again.
What was done?
Still, it's just hit 420. I tell you, it's winding us up. One 121. Now I understand why it overshoots. Puts in a load of power to get close to being there, and then it turns off.
I can see your steps here.
No, it's nice data.
You could have stayed here.
We could have stayed here, and it would have been too little, too much. Still too much. Oh, hold on. starting to look like it's dropping a little. Or am I making it up? It's a shame in your software you can't force it to average it a little bit longer.
Yeah.
I can do a 10-second average.
Probably I could, but I don't want to.
No, don't change anything now. No, stop no, no, stop it. Don't even think about it. I don't know why you even thought about it. It's definitely looked like it's crept down a little. Oh no, it's gone up again. Right, I'm going to take it down to 118 or less. What? It's gone up.
17.
Yeah, 117 watts. Because see, the challenge with the thing is that you're trying to get one side at a temperature and the other side is having some crosstalk. So over a period of time, it's going to, contribute to its heat, even though, that is the challenge with it. So I'm going to bunch it down on a sensible drop now. I want to watch this drop below 400. I mean, I can see the response over here. Look, oh, there's a response. That's kind of what I know it's dropping. Not a lot of drop here, more drop here. I went to 101 watts. Oh, it's definitely looking like it's going down a bit. Or not. Yeah, I think we can even go down more than that. I'm going to be bold. 90 watts. There we go. We're all the way up there at 150 watts. Now we're at 90. Fast response over here. Come on, this is more like it. I can actually see a trend line that's going down now.
Probably too much though.
Oh, come on, you skeptic. You skeptic. I took off 40 watts, 50 watts, 60 watts, 90. We're back down to where we were a long time ago. Like, we're back down to where we were here. Where are we? Here. Back down to where we were there. There.
That was the energy to heat the block.
That was the energy to reach equilibrium.
Okay, we are close, so you might want to dial up.
I don't know. Let's sit there for a while. Looks like it might go under. And there we go. So we'll go up a little bit. So
Maybe I can go here where it was just a straight.
where it was flat.
Yeah. Like
So that was about 130. It's quite a bit.
Yeah, 30.
Okay. It's still falling. So 101. We're back up here. It's going to get easier. This is going to be the hardest step.
Mhm.
Oh,
89. Mhm.
it's not easy being the PID. Giving all your energy to just one reactor. That's my worst Dolly Parton impression ever. It's not easy being a woman. Giving all your love to just one man. Did I do it worse? Ah, Dolly.
Getting after all. It's got
You know, artifact, we don't actually have to be exactly on 400 because maths can actually play with different numbers, right? It can be like this is notionally the 400 degrees, and when we see it stabilized, we can say that's our stable temperature for this number of watts input, and this is what we see on the
Yeah.
Dwyer. And the Dwyer's looking around about 179, 180 now. So 180 translates to 400 in the core, approximately.
if the line stays straight.
If the line stays flat. So my actual desire right now is possibly to walk away and come back in 20 minutes when I've warmed up.
Yeah.
Because this is looking pretty flat. Yeah. Whatever it gets to.
It's rising a bit, but not too much.
And the trend is up slightly.
Yeah. But not
So shall we just tweak it down to 120
Mm.
and then walk away
Yeah.
and whatever will be will be. Otherwise, if we tweak forever. 117, that's a nice number too. Right.
Mhm.
All right. We have to step away, guys. Thank you. Good morning and peace to you, keepers. We'll be back in a little while. Okay. The basic media and stuff. The new MacBook, whatever it is, near $600 it's called. Right, so we have decided that this will be our first recorded point. So it's not the active internal is around about somewhere between 414 and 420. 413. And really, it's kind of like 413 to 420. It's around about the middle of the line there. It's 416. 416. Approximately 416. The control internal is around about 384. That's actually more stable right now. He says about 384.
Yeah.
And the Dwyer is fairly stable, pretty darn flat at about 194.
96.
Oh, sorry. What was it?
You can look that.
Oh,
196.
yeah. Okay. Yeah, 196.4. It's pretty solid. 196.4. 196.4. Now, do we want to take the
What?
the control is 194.5. It's quite close, isn't it? I might need to do a new table. Let me do a new table. It's a bit bigger. So I'm going to do this way. Act, int, act. Dwyer and there's control. No. Control field. And to the internal is 416. And that's 300. 6.4 the control is 194. Hold on, then my
95. Okay.
194.5. Okay. So what we are going to do now is we are going to attempt to raise this up to something that we think will achieve something of the order of about 500. Any prizes? Guessing what? What do we think?
500.
Yeah, what do we think? 100. We know the full range is, what was it yesterday?
400 something?
Yeah, so I know 150 watts. Because remember, we don't need so much to go.
But you need always a bit more.
Okay, so we'll try and overshoot to start with to get the bulk of the material higher. So let's go to 170 watts.
Okay.
That's a bit too much.
Yeah. Good.
173, let's see what happens. No, the highest we took it before was 150, wasn't it?
Is it- We have to change it anyways later.
Mm-hmm. Forty. Still going up pretty sizably over there on the hot spot. So 100.
Not a real curve. It's just go straight up.
Yeah. It's funny because it shoots up at one angle and then it curves and it shoots up at a different angle. Yeah.
Let's go.
I do like the fact that temperatures between the Dwyer and the control are looking quite close. Actually, now.
Yeah.
Very close in fact. Okay, we're starting to get a bit of a tail on that. Uh, I'm very used for the hotspot. I mean, it's only indicative, but it's nicely indicative. You can start to see the curve on it quite quicker, quite a bit quicker. So 75 coming up for
Oops. Might be one shot.
Will be pretty impressive if we could. It is trending. I think it's going to overshoot, but then, yeah, the other one was overshot anyway, wasn't it? So, yeah. Oh, and that was. I need to put then watts on this. Yeah,
111.
just 111. My best time. No overshoot. By how much? Definitely less noisy. You're trying to do it with your fingers.
Yeah, the yellow line,
Yeah.
it'll take to go over 500. I don't think it will reach it.
No, the yellow line's not going to
Yeah.
reach it. There's the red line, isn't it? But the red line's basically on the line now. It's whether the yellow line, red line straddle the 500 mark
Oh,
as we had before. Yeah, the 400 mark. Yeah. I mean, the hotspot is still rising, which is an indication that we're still going to be rising.
mhm.
Yeah, what I'm saying is that over here, you can see that it is still rising, but not so heavily. For those that are looking now, these active in control are dud because they're actually below 150 degrees centigrade. So they read erroneously. The only thing that's useful currently on this is the hotspot, which is only indicative of a change, and it gives us a very fast response. So we can see something's happening. So I'm tempted to dial this back to about 165 now that it's punched through 500 quite clearly.
Yeah.
So I'm going to bring that back. A little bit more use.
That's why you need a big cardboard to be more precise in the dialing.
Big lever and you just move it a little bit. Yeah. Not far off. There we go. Yeah, this one's flattening off here.
Yeah.
If it might be even trending down slightly. It's good. This is what we want.
Good.
Yeah, it's pretty flat. Does that translate to some flattening off on the Dwyer? It does look like it might be. Not bad. Really want to wait until the wire and control flatten off as well. These ones will flatten off quicker uh, here because there's less thermal, delay in the heat coil to the ports. Whereas, yeah, this is going to take a bit more time. We're actually starting to get to a point where we're starting to see some temperature in the active control area here. It's not stuck at the minimum. I'm working to what everyone agreed. All right, well, we can leave this to settle out now. I think it's going to work out quite nicely. We just need to have the Dwyer and the control lining up. In a while. So we are back, and it looks like we've got our second calibration point around the 500 line. So if we gather all our relevant data here, so the watts are 144 watts. Our active internal is pretty stable, really. It's about 518. Pretty darn flat. I'd say rounded up, that's about 518. Pretty solid.
Look at active and control, they're the same.
Wow, that's pretty impressive too. So okay, so the control internal is 480, I'd say. See, yeah, 480. The Dwyer is sitting at what is that? 256.9. Really solidly there. And the control is sitting at 256.5. Yeah, 256.5. Much less fluctuation on all of these right now. Okay, so Don wanted to use AI to see if we could work out what our next input power would need to be to achieve the straddling of the 600 line. So I don't know. Hello, Corky Goss. You're lurking, are you? Hello. We just had some wonderful fettuccine with some grana padano and some. Do you think they're from Germany or they're Italian? There was tartuffe like cream, wasn't it, with the fettuccine?
I didn't look at the.
Oh, well, definitely the actual slices were from Italy. Very nice. Thanks. Okay. Happy Easter, everyone, again. Yes. Wonderful. Okay, so do you want me to ask Grok?
Yeah.
Let's see if Grok has an idea. So we'll do expert. If I have a heating system and I am trying to control it with power in, and I have two data points. The first one is at 111 watts, and it achieves a temperature of 416 degrees centigrade. And then a second data point of 144 watts, which achieves 518 degrees centigrade. At what power input would I need to achieve approximately 620 degrees centigrade? Okay. So
Thinking.
I'm asking Grokkage here. I used Whisperflow there to talk at my computer, and right now it's trying to work it out. So it's proposing a model and trying to use the Stefan Boltzmann to calculate the power that I need to put in. So it's fitting a linear model. The fit yields exactly 177 watts. Really?
Linear model.
Okay, approximately 177 watts. Okay, that's what it said. Based on Stefan Boltzmann. Yeah, to rise another 102 degrees centigrade, 518 degrees centigrade to 620 degrees centigrade requires another 33 watts to take it from 144 plus 33 to 177.
Okay.
All right, let's see if it's correct. Now, do we want to overshoot and come back down? Do you want to take it to 200 to try and heat the bulk? And then come back down to 170. Yeah, it's going to get us there faster.
Maybe not too late.
Right, so I'm going to go to 210 in theory. something over 200. 211 there. We're going to leave that for a little while until we start approaching our power point. And then we will dial it back to the system suggested, or the Grok suggested, 177 watts. It'd be nice if it was 111, 144, 177. Yeah, Forky says, that's my way of thinking about those chronicles. Currently trying to see Noah and the Ark in the new light. Thank you. So, on its way up, attacking that thermal mass. I'll dial it back to the plane 177. If it gets it right first time, that'll be pretty impressive, I have to say. Finally, a decent use for AI. Better than our random stabbing in the dark, fiddling for the first two power steps. Now, the most important thing about this whole process is to ensure that we don't take the temperature of the core over 159 degrees centigrade in an active run, because we don't want to melt any copper. That's the most important thing.
1059.
1059.
1059.
1059.
Thought you said 159.
Did I say 159?
I thought
1059. I might have said 159. I'm just still thinking of the truffle flavour in my mouth, and everything else is like partially irrelevant. Yeah, it's on its way up. Turtle is sitting at 572. I mean, we did do something similar to this in the last step, didn't we? We went way over, and then we pulled it back. We went to 150. We went to 150, and then no, in the first step we went to 150 and pulled back to 111 to get it to sit.
Yeah.
So.
And you would soon dial back.
Yes, the human PIDs here, but I say we could probably class ourselves as AI controlled now, or should I say AI controlled? So we just dial it back to 177 and walk away and pray. Right, it's getting to our 590, so I'm going to pull it back now.
Right.
And we go for 177.
79. Oh, 78. 77.
So it sticks there. 177. So here is the moment. We can see over here on the Optris, the hotspot, our trusty indicative hotspot.
If you click the mouse, you see it.
We are pulling back now from our trend, and it may be flattening out. And that's kind of what we want to see. Oh dear, it's gone up to 178. Back at 177.
I think we are.
What were we targeting? I don't think it's right.
Yeah, no.
I think it's trending downwards right now, and that's the problem with having
2 data points.
2 data points.
Yeah, can add something. And
Yeah.
that's 20 watt more.
You think so?
Mm-hmm.
What did we have it on before? We had it on 200 and it's definitely flattening off, isn't it? It's very much more responsive at this. You can feel the control a little bit more. Yeah. AI epically failed. Clearly it was wrong. So I'm going to dial it up. Give it another 10 watts. Look at that. Freaking genius. I mean, just one touch of the fingers, and we've got exactly an extra 10 watts. Our FOSS response indicator over here is pointing to a little bit of a growth, which is good. Is it going to be enough to push us into the 620 range? I don't mind if it needs to be straddling the 600, but yeah, I'm kind of minding to join you in the adding another 10 watts. So we'll take this up to 197. So it doesn't be as lucky the second time. I think I might not quite got that one.
97.
Not enough. Too cautious. Okay, that was a 2-hit wonder. Of course, we'll eat our words if it continues to creep up, and then we have to dial it back to 177 to stabilise it. Be like, damn you, AI. The deep irony would be if we end up exactly at 210 or whatever it was that I said it to first time around. And that was just the intuitive guess of myself rather than AI's calculated nonsense. There's definitely some up creepage going on, isn't there? It's a fairly steady clip of up creepage. Damn it. We might have to dial it down. starting to level out on the
Mhm.
fast response signal over here. And over here we have still, it is 595, 596, yeah.
Trend indicator. Sure.
Mm-hmm.
Moving on. I forgot how many
How backward
values
looking
there.
it is.
Yeah.
Mm-hmm. Mm. What's the measuring?
185.
Oh, great. Like what it
Seems
should do.
yeah.
Yeah, pretty much. Yeah. I think that part is nailed in terms of a data point. Happy with the power monitoring, really happy with that. Thermal imaging is working, power monitor is working, and now hopefully we know the parameter space in which we can use these thermocouples without them epically failing. Which I did last night and scuppered our plans, our well laid plans. Imaging a nice crisp 1.501 amps, 1.5 amps, nearly. Still trending up. That AI is starting to snigger in the background, I can hear. Scan. You should have listened. It's going to be 177. And I think it's 197 watts, but I think it's going to be 177. It's definitely trending up, isn't it?
Yeah. It's 177 went down, so can't be correct.
Yes, it can. That's the whole point about Stoke and Boltzmann. You haven't got the full amount of losses. And because you've only heated up part of the bulk, that gets lost. And so it goes down because you're putting less power in. So the temperature's averaging out through the bulk. It's calculated this up that the system is losing a certain amount from a certain area, which it doesn't know. And the two data points are pointing to that. I think that's just going to keep creeping up as the whole thing becomes into thermal equilibrium. And we're going to have to dial it down. We're going to might even have to eat some crow. The reason that went down, I'm telling you, is because you had a big thermal sink. And when you turned the power lower, it was still equalizing. And so it was spreading that extra thermal energy out.
Measurement was closer to the heating elements.
Just
We'll see.
I think that's clearly going up at quite a clip, and it's going to continue to do that.
Short time. Maybe you can see.
You want a longer time? Yeah, that's right. Yeah, that's clearly going up. That is going up at quite a rate. It's even still going up here.
Mm-hmm.
And again, the reason is that this is very fast in showing its response. It went down very quickly, but that's because it's got lots of colder material to suck up the remaining heat, and so it then can't maintain its own heat for longer. So yeah, this is sad as I'm going to say is I'm going to turn it down. And the question is,
nearly there.
what?
Yeah.
We're nearly at the target temperature, and it's still going up at a rate of knots. All right. We should have just put it 177 and walked away, but at least we're getting to
Damn you, AI.
I'm getting good at this. I'm still going 10 watts higher, or 11 watts now. I don't know. It's still going up a fairly hefty clip. Now again, it's the same story. It's just less extreme. But back here, it was really extreme because it had all of this mass to sink its heat into. The rate of climb will drop, and then it'll start equalizing, and it'll slowly creep up, but it'll be creeping up slower rate than this. Anyway, if it's going to be 177 by its estimations, and the previous ones were 111 and 144, I think it should be 188. Can't be 100. We can't have 187. It's got to be 188, not 177. You know, it's good. Yeah. It looks like it's going down, but again, it's the same story. It's just a slower story. So I think we walk away and we come back in half an hour, 40 minutes or something. So we can do something else. As much as we love being with you guys, all 9 of you. It's pretty steady at this point, but it might be going through that dip and then coming up again. Look, you had this initial big drop here. Right. And then it's kind of still dropping a bit and then it's leveling off. And then you've got to ask yourself, is it going to start to creep up when it comes into equilibrium? Okay, let's do that. Let's walk away. Come back a bit later. Okay, we've come downstairs. Reason being that it's still trending up, isn't it? Of course. So the question is, do we give in and say if it was correct or not?
Oh, wind. When we came in.
It's probably just our airflow around
Yeah,
this equation. So
it's not 20 still.
it's well over 620 now. So do we want to split the difference? 177, 188. Do we accept defeat and put it to 177 or
82.
I'm not calling that is not an average at 100, 620. It's nearly hard above 620 now. It's very close. Did we lose a couple of watts? It's very close, isn't it? I do like. I do. It is still flying. I do like the idea of 188.
It's just going up.
Yeah.
But over a long time. But it is.
Okay. I'm gonna lose 2 watts. Is it going to be enough? You know, this is not ideal. I can feel quite a blast of cool air.
Yeah, I thought about that
Yeah,
earlier.
that needs to be resolved. We're doing a lot of learning here.
Yeah, true.
What I'm saying is there's a fan keeping this cool and it's blowing cold air this way, which is affecting this side.
Yeah.
Yeah. Okay, look at that. It's hard over 620 now. So I'm going to knock a couple of watts. Or 1 watt. It wasn't as responsive as I was thinking it was going to be.
What to say? Maybe 5, but probably not too much.
Go now gone below its recommendation. That's not going to be any good. Stop it. 183.
Yeah.
It's trending down at the moment.
In the settings, there was trend window size, and it was 40. So 40 steps, 40 seconds. Trend.
Does it have a trend flat?
No.
Right. Because you've got to have like a significance level for it to be, because you want to know whether it's a trend flat over 40. It's pretty good now.
What to prove? Wait, what can I do now?
Because this is flat. This is dead flat now,
Mhm.
pretty much. 461.5, 5, 6, 4, 5, 6. Yeah, that's pretty damn flat. This looks flattish.
No.
Still says it's trending down, but yeah, I'd agree it is. Very slightly. What is not trending anywhere, although it says it's trending up, is the active Dwyer. It's hard locked at 324.9.
Mhm.
And I guess that must be an average over a fair amount of time, right? Because it is so odd.
It has just one decimal.
Right, yeah. Oh, that's just changed. 325. Now the active internal is trending up. And it's at 619 or was. Now it's trending down. Right, okay. It's going up and down now, so I think we might call it. This is the 620 point. So AI was wrong. Can we just clarify, everyone? It was wrong. And it was not just wrong by a little amount. It was wrong by a lot of amount. Which, like, it said 177. And actually, it's 184.5. 185, thereabouts.
But the next guess, maybe.
Yeah, it looks like it's 184.5. It's flitting between those two. Yeah. So, active internal. 4.5. Way out. It was way out. It wasn't even close. uh, right. So we're calling this. Is it? Oh God, is it 620 now or not? I don't know. Yeah, it's 620, 690, lower, 619. Oh, I'd say more 619. All right. Control internal is 578. 578. The Dwyer is 325.3. And the control is 327. 327. Point 1, 2. To 7.3. Okay. Right. So we will add. Firstly we will tell AI how wrong it was, because it's going to care about that. Its feelings are going to care. Actually, to reach 619 degrees centigrade on this power step, it took 184.5 watts. So bearing this in mind, with the previous two power-driven thermal temperatures, can you calculate the amount of watts necessary to increase the temperature to 720 watts? Oh, that's not going to work. I'm sorry. 720 degrees centigrade. Not watts.
Yes.
Radiation effects may affect watts. Linear regression to fit all 3 points.
That's good.
It has useful data to work with now. Very difficult. Very difficult to. You've got a curve that fits with R squared 0.9977. Not bad. Not bad. It's saying 246 watts. That's his initial estimate. What do you think?
Go for it.
It seems to be the radiation model seems to fit that. And now it's saying the linear regression, 220 watts. Now it's fighting with itself because it's in expert mode, no less.
Thinking. Okay.
Right, it readdressed that.
Solve it.
So it thinks 220 watts.
Sounds good. Good.
Says the small deviation you observed, the 2-point linear prediction of 177 watts for 620 degrees C was a bit low. Is already captured by the updated 3-point fit, which averages the slightly decreasing slope across the full range. The fit remains excellent, so 220 watts is a reliable extrapolation under the same conditions. If you collect one more data point or have details about the heater type, e.g. whether radiator losses become dominant, the estimate can be refined further. But with the data available, this is the most accurate simple calculation. So we're looking at 220 watts. Is the AI going to be more accurate than its near epic fail on the last one? We shall see. Right, so 220 is the order for the day. We are raising it by 45.5 watts. So 220.
Do we use more power at the beginning?
Yeah, I think we do. So let's put it up to 250. Yeah. Not 287 or 317. So what we're doing here is we're using a little bit more power to increase the bulk temperature so that we can achieve the target stable temperature sooner. So we'll dial it back after we see it exceed the target temperature, which is 720 watts. I won't write it down now. It might be different by the time we settle. What's the scale? Before the initial curve is because it's still trying to heat that block of material up. That little robot is sucking the energy that's been put into it. No. I think it's not going to get there. It will. A very strong rise over there on the friendly hotspot. Something I thought would never be of use, but really is. It's indicative of trend. Seeing a bit of glowage.
I want to see it.
So the crack is
Which is a white form now.
On this side.
Yep.
Mm. Yeah. Yeah, that's a big problem. Yeah, fan.
Yep. Mm-hmm. There needs to be a shield
Mm-hmm.
between the electronics and
Yeah.
the rubber. Maybe watch it. 700.
We are. Let it overshoot.
Mm.
250 watts. So it recommended what?
220.
20. Okay. Well, that might be right, you know. It was wrong before, but to be fair, it was only a 2-point fit. You can only do a linear curve, which is not a curve. It's a lin. It's a lin. Hmm. 690.
Yep. I think it's 700. Probably.
No, that should.
Yeah, more.
Yeah. So it's dealt with warming the block now
Mm.
a little bit more.
Mm.
Oh, the suspense. This is mildly more interesting than watching paint dry. Here we go. It's going to bust through that level. And it's still going up at a fair clip.
Oh, yeah.
So, yeah, it's definitely not the right. This accentuates the problem because you've got a hot thing here next to a cold thing.
Mhm.
Right. So it hasn't reached an equilibrium in terms of the power into the power loss. So this is a good indicator that we are not going to we're a bit far away from where we want to be in terms of the input power. So we bust 700. The question is, do we get to our result faster by letting it over? Which I think we do. Let it go a little bit longer. I'm thinking that the reactor moved a little bit, given the fact they're slightly offset. Yeah. Anyway, that isn't critical for this particular.
Maybe the coin.
Maybe. Please put them on. No, the screen over there. Right. So let me get to 705 and then we'll dial it back. Well, we hit 705, so I'm going to dial it back to 220. We'll find out if the AI was wrong. Again.
When we approach.
Just trying to creep it back down to 2.
Yeah. Oh,
I mean, I like 2. But then we're not giving AI a chance by actually giving it the number it wants.
Yeah.
What do you want to do?
Go down.
Right. We need to prove it wrong first. It's not that we care that much, but, we need to know. Wait. And breathe. Okay. Yeah, it does look like it's going down. Mhm. It'll level off and then it'll creep up a little bit. I suspect that will be the case. I have to say we make a better PID than the Dwyer.
Yeah.
2 humans, and you see, you can't get rid of manual labour.
If it goes up again.
Well, there's the thing. Definitely got a permanent trend down over there. I think he got it wrong again. I hate to say it. I mean, I don't hate to say it. Quite good to say it, but well, there's the thing. There is the thing.
Oh, you said no. So what?
It's creeping up by its own accord now. No, 2020. Sorry, what was you saying?
I thought you wanted to say something.
Um, it's still trending down.
Yep.
And our hotspot is starting to level out,
Mm-hmm.
which is good. I just don't feel it's got that quite right.
Mm.
So
Maybe because of the airflow, which is not.
it can't account for. Yeah, I mean it's got issues that we can't account for.
Mm-hmm.
The fan isn't changing, but so is it creeping right now?
Okay. That takes a while.
Hmm. How much out was it last time? It was 7.5 watts out. I think it would be more because it's going to lose heat.
Mm-hmm.
I think we're going to have to give it another.
Mm-hmm. Like 20 again? No.
No.
What did we do last time?
Well, we ultimately ended up 7.5 watts over. Now, as it gets higher, the relative temperature losses should be faster, but that should partially take into account. But it's definitely still trending down. So I'm going to kick it up another 8 watts. 8 watts. Not that. The other challenge we had was the actual ambient temperature in here is dropping.
Dropping?
The ambient temperature. Yeah. Maybe not at that thermocouple, but I mean, radiative losses.
Mm-hmm.
Okay, so we've got a trend up now. And this is not too aggressive over here in terms of the trend up.
Yep.
I think we can walk away from this a little bit and let it settle. Yeah. we have established that that AI is useless. It is totally pointless because it said to achieve 720 degrees, we would need 220 watts. We're 228 watts because we didn't believe it. 712 degrees. Granted, it is going up at the moment, but it is going down a short while ago, so it's pretty stable. So, further ado, we will do this. We'll ask AI to make a better idea of what's going on, and I expect it to fail again, but well, it should be better. So, the watts here are 228. The active internal is about 712.
Yeah.
The control internal is 668. No, 669. 669. 669. The Dwyer is sitting around about 400 dead. And the control is 402.5. Yeah. Right, so see, now I can make a better match this time than failing in the last two attempts. That step actually took 228 watts to achieve a temperature of 712. Given that, add that to previous datas and try to calculate how many watts we would need to use to achieve 800. I hit 800. I don't want to go too high in these two steps.
Thank you.
Why do linear fit the whole time? It's still doing linear fit. Honestly, it's not even attempting. With 4 empirical data points, you've now provided 111 watts for 460, 144 watts for 518, 185.5 watts, 184.5 watts for 619, and 228 gave 712. The relationship between input power and watts and steady state temperature remains very well described by a straight line. No, it doesn't.
Yeah.
It's not even attempting, is it?
Maybe you can ask or tell it. But it's not really a straight line. I would think.
It's gone from 2.75 degrees per watt down to 2.51 degrees per watt. side. So I think we'll go for 300 watts and dial it back to 270.
What
Because
does it want?
Hmm?
What does it?
260.
260. Yeah,
Okay, so 300. One I'll do for now. It's just I dial it back to 270. It seems to be a little bit out, but the thing is, we've asked it to try and achieve 800. So I don't mind being a little bit over.
okay. Yeah. Yeah.
It's actually saying here to rise another 88 degrees C, 712 to 800 degrees C requires an additional 35 watts, which 228 plus 35 is actually 263 watts. Very close to the 4-point regression result.
Okay.
So it's sticking to its 4-point regression result, even though it's calculated that it actually needs, because of a change in slope, 263 watts.
Yeah.
So we're going to give it 270 because I don't mind being a little bit above, settling out on that. So we'll try and see if we can punch through 800. Because 800, the reason I'm wanting to stop at 800 at this, ideally, is because that is the temperature at which the thermocouples start to fail.
Oh, degrade.
Degrade, yes. Anyway, the Dwyer set points here for our active internal is approximately 200, 250, 325, and 400.
Mhm.
So these are like 75-degree steps for these two, roughly. Question is, without changing anything and putting this on full cold, can you let it cool down? And let's say tomorrow, just see if we can target these temperatures by setting the Dwyer at these set points.
Yeah. Right.
If it works the other way around,
Mhm.
whether it just decides not to achieve the temperatures.
Yeah. Yeah. That's a different problem.
Yeah. Then we'll know if it's actually this.
Mm-hmm. The setting, maybe.
Something.
Yeah.
Something's all right. Zem, zem, zem. Level 91. The other thing is that under this scenario, you see a very, by changing the PWM, you see a very good regular power here.
Yeah.
So you can actually set a power.
The set point should reach temperature X after the execution time T. So it tries to get to the correct temperature, and because of the wadding, it has so much delay that it's not working correctly, I think.
And then just give up. It just gets to a temperature and stays there.
You can set different patterns, but I'm not.
Yeah. That might explain it, that it can't. It's not achieved it, and so it just stops at that point. So 96. So people on Artemis are getting their emergency suits on, their blimp suits, which allow them to live or breathe with a punctured spaceship for about 6 days or something. They can eat and stuff whilst being in these suits. So they've had to reconfigure part of the internal ship. It's quite interesting because they pack everything away. Like they pack the launch chairs away and everything so that they have more space inside when they're actually trying to exist in there. They are going to have lunar closest approach in 1 day and 12 hours, 37 minutes. And according to this data, they are 354,000 kilometers rather, from Earth. Now, much closer to the moon, which is just 102,000 kilometers away. So, too shabby.
I
think they're actually slowing down at the moment. 2,503 kilometers. Earlier today, they were traveling at 26,000 kilometers an hour. So, their trajectory correction 1. Next one is 2, and the next trajectory correction within 2 hours and 35 minutes. And just over a day from now, they will enter sort of lunar gravity sphere. Meanwhile, back to the main event, of course. Not going to the moon or anything. We're just, we're using far less power than that device as well to do what we're achieving here, which is warming up a little robot. A mere 300 watts. We are exceeding 800 degrees right now, and so we're going to let it shoot over a little bit to try and bring some of the bulk of the little robot up to temperature, and then we're going to dial that down, not to the 260 that it suggested, or even to the 263 that it hid, that it had actually calculated, but I think we'll put it down to 270. We were 7.5 over on the last one to achieve the actual temperature we wanted, less 1 degree. We were 8 over to achieve 8 centigrade under, so we're going to go 7 over or 10 over and see if we can achieve something around about 800. Well, we've learned a lot, and we've learned quite possibly how to make a device that can do an experiment without falling apart.
Yeah.
If
the crack is not developing.
Well, I think that's less important because it's factored in with the temperatures that we're measuring here. Doesn't seem to make that much difference. I mean, when you think about it, the crack is, it's most of the heat's inside the coil, isn't it?
I mean, if it doesn't fall apart. But we can glue it together.
Yeah, we have the means to do that. We don't have the cheesy lounge music in the background unless we strip it from the video.
Yeah.
We're talking about the late Alan Smith discussing how you can fix a little robot with some of the same cement that's used to seal the reactors. So I think maybe if you, in the next couple of months, can find some time to process the fuel, then I find a convenient time to come back and we actually do an attempted run. You're going to have to rearrange everything here. I might take a few components away with me, like my webcam and the thermal imaging, but that doesn't really affect what we need to do to prepare the fuel. You could do basically nothing and just use what is there.
Yeah.
That would be the quickest. You might consider preparing more on the dial pad, since once it's done for as many as you do, right?
do have enough of that.
Yes. Uh-huh. How many are actually on one of those 3M pads? You're going to count now, aren't you?
Many.
Many. That's a technical number, isn't it? In engineering terms, many.
More than 300.
More than 300. There we go. It's a simple part. Okay, so we've got 11 degrees over our target temperature. Technically, it would be nice to be split the difference with the active internal and the control internal like we did on some of the earlier things, but that's not so important at this level. It's more important we have the calibration point without breaking the thermometers. And we're going to do one more after this at roughly around 900. So I think we're going to dial this back now to 270. He doesn't want to move from that. Oh, the light number 272 as well. I'll leave it at 272. That's 9 watts above its hidden estimate. It wanted 260, but it hid 271. Okay, right, fine. It was suggesting 260. It was hiding a 263 figure in its calculations. And here we have something between. I'm gonna make that 273. It's drifting at the moment. Now you go up a lot.
We want to stable.
I want it to stay solidly on something. I don't want to have to make another, just stay on 3, 4, don't care which, or 2 would be fine. Or 1, if you must. Just stay. Bit of glow on the tubes now. Over there. I think we leave it to settle out. Yeah. Whatever it is at this one, I'll be happy with. Just going to take some time. It tends to take about most of the meal.
Oh, that takes longer every time.
Well,
Sometimes it's quicker.
turns out intelligently we are working. And trend down and then trend up a little bit, I guess. When we say trend down and up, here you can see this little green arrow, and that's indicating a trend down at the moment, which it's maintaining, but that's fine because it's about equilibrium. Again, you can see here on our indicative hotspot that this comes down quickly, but then it levels out, and you will see it come up a little bit, probably. So
I don't want to lose too much temperature.
and what are we are somewhere between 9 and 7 over. Maybe we should make it 275, around 275. One more point before we feel like we need to tweak it again. We'll make it 275. It is very tempting, but we want to get one more step in before going to sleep. So we need to encourage this one to step into action a bit more. 276, that's fine. 4-5, make up your mind.
It's getting.
Mm-hmm. Okay, so the trend has now shifted to going up slightly.
That's okay.
Yeah, that's fine. And here we can see it's flattening off, if not just a slight trending up now. It's good. Just want to try and achieve somewhere between 800 and 810, 20, something like that on this one. And just say the AI was wrong again. Still trying to fit 4 dots to 4 points to a linear curve. It's saying it's not a linear curve, but it kind of mostly fits a linear curve. Like, okay.
What are 7 watts, anyways? Comes up with slow.
Yeah. It's okay. Ryan, how not to oxidize your thermocouples so that you get fake excess heat.
Some bigger jumps now. Was so? Yeah, yeah, 98, and it was 95 seconds ago.
It's pretty flat over here, isn't it?
Yeah. Yeah. Sticky.
Down.
Yeah. So, jumps.
Maybe that impressive.
Just
Flat.
mm-hmm. Okay.
Still thinks it's trending up, but I'm not overly convinced.
It can be whatever. Doesn't.
Oh, there we go. At 8.5. 8.7. $7.99. Yeah, that. I think we need to step away.
Yeah. My mind.
It still says it's trending up. Well, be 99413. 99354.
Down. Sure.
Why do you choose green for down and red for up?
Red heat.
Yeah, okay. Why not blue for then down?
Sometimes depends on what type of thing.
It does, doesn't
Sometimes
it?
it's better.
Yeah.
So I couldn't decide on. It's just temperature.
A choice has to be made.
Yeah.
Yeah. Now it's going up. So much for the AR. 206. With 276. Pretty flat, isn't
Yeah.
it?
I can see. This is also totally.
Yeah, so we're gauging two data, kind of like impressions. This one is pretty darn flat.
If you have to click.
Yeah, pretty darn flat here. Okay, not really what I would call. I can zoom in to see the trend a little bit closer, but really that is there may be a little bit of an uptick here. But it's not massive. Interesting note that this is now 601 degrees on the outside, and internally it is nearly 800 degrees. So earlier you saw these things as being much warmer, the internal temperatures, because you're looking at the temperature of the wire, because now the wire is, or something that's close to the outside, but now inside is able to get to a much higher temperature than the instantaneous temperature on the outside. It's around about 798, isn't it?
Yeah.
Okay, I think we'll call that. So not at 260 degrees, but at 260 watts, but at 276 watts, 276. Suck that, Grob. 797. And the control int is about 759, I think. 759. Dwyer was 76. And the control is 418. 3. Yeah, 483. Okay, so I'm going to give you one last chance. You've got 1, 2, 3, 4, 5 data points. Right. Don't give me another linear assessment, please. Hi, Mr. Hall. How are you? So it actually took 276 watts to achieve 797 degrees. Holding this in mind, compared with all the other previous 4 steps, can you calculate how much in watts it would require to achieve 900 degrees centigrade?
Thinking.
Not much that. Bearing in mind its last step was 5. Raising at steady state temperature continues to be very well described by a straight line. Come on!
Tell him that he was off every time. How could I say that?
Now it's saying a straight line gives it 314, but actually use 320.6.
Why? But yeah.
And you try to hit a curve 2, 5, 8, 1, and 3. Maybe I'll give up on the straight line idea. So there's 5 data points. Just draw a straight line through it. That's all you need to do. Using a quadratic polynomial fit. That sounds good. We like that. Come on. Sounds like a much better idea. What did it say before? It said 320. Now, with a polynomial fit, it's saying 340.
Wow. Okay.
I'm actually believing it now.
Yeah. That's better.
I think it might be because it was obsessed with drawing straight lines. Obsessed, Grok. All it wanted to do was draw straight lines. I said, draw a curve, go on, draw a curve. And it did. And again, it's 340 watts, not 3 points. So, I think we go to 360, get close, and dial it back. In fact, it says, otherwise, 340 watts quadratic or 348 watts radiation style are the most accurate. I think probably 348 is going to give us our number. So, because we're on like 276 now, because we're going to get more radiation losses. So, let's pump it to 360. Hit the mark and then bring it back to 348.
14 degrees too much was good.
Yeah.
About.
So we're going to go 360 and bring it back to 348 and see if the AI has finally done something useful. Because it got told. Enough of the straight line. Enough of the straight lines. Of course, we're in thermocouple degradation temperatures here. So we don't want to do this too long. Okay, somewhere around 360. I'll do 360 then.
Was 900. Yeah.
Mm-hmm. Here we go. Why the curve fit matters. It's still ramming straight lines down until it says stop it with the straight lines. It's why the curve fit matters. The data show a clear non-linear trend. Why were you still trying to fit a line to it then if you could work out that it was showing a non-linear trend? Each successive temperature step requires more incremental power per degree C than the one before it. Well done. Well done. This is exactly what a quadratic or radiation-dominated model predicts, because heat losses, especially thermal radiation, increase faster than linearly at higher temperatures. Thank you. Thank you. I've only been trying to tell you that for the last several hours. The earlier linear extrapolations, therefore, underestimated the power needed to be at 900 degrees C. Wow. What a surprise. For completeness, a physically motivated alternative model in the form of P, that's power, is approximately equal to A plus B T capital T plus C T to the power 4, approximating conduction, convection, and radiation, fits the 5 points even marginally better. Huh? R squared is 0.999964. That's pretty much better than the nonsense you were feeding us earlier. And predicts 348 watts. Only 8 watts higher than the quadratic. Both curves agree that you will need noticeably more than the old linear estimates of 314 watts. Yes, thank you. If you supply one more data point near 900 degrees C or details on the heater type, e.g., whether it's a resistive element in a furnace, right, sort of, the curve can be refined further. Otherwise, 340 watt quadratic or 348 watts radiation style are the most accurate predictions on the data you have. Sorry, I think it's going to be quite close to 348 watts. I think. Achieve 900. Where are we now? We're at 857 and rising. Finding some use. It's gone off the chart there. Just got to remember to hit the continue on here. Otherwise, it gives you a freeze spot. It's quite nice the way that works because you can drag around it and automatically assumes you want to look somewhere. That's something you can learn from. Right? Yeah, I want to look at that bit of data. Drag around, and then it auto resizes. No, this is a good way of doing it, but then you have to remember to click too. But that's, yeah, quite good. The good news about finishing this calibration at 900 is that we can go to bed. And we don't have to be surprised at 15 minutes past midnight that something ridiculous is happening. And then have to work out things about LabJack Pro and
And I don't have to
thermocouples.
freeze in the basement in my pajama.
Yes, also that too. Yeah. But we missed our call with Matt. I mean, we completely forgot about it because we were having dinner.
Well, I didn't know what time it would be.
Maybe we can contact him and see if he's available in the morning. That might be a useful thing to do. Hmm. Scan that to something. might make this just a little bit higher to accelerate it because we want to dial it back to 348. Yeah, with this method, you are scaling horizontally and vertically and setting the position you want to see it grow from and then putting it to continue. So you're setting the size of the window and the scaling factors.
But then it can grow out.
It can, but then you could also, it has this button up here called global, and that shows you all of them, and then it will keep it in there when it's global. Of course, when in your system, if you turned off a couple of things, then it would be global for that.
Yes, I can.
Yeah. So the combination of what it's got here and what you've done is not a bad way to go.
I think you can disable it in the other tab, but
yeah, not now. Not now. Yeah. Can you plot a chart in latex code based on the data you have using the radiative heat loss physics model and place the result as latex into a code box?
Thank you.
I'm already paying for it. I don't have to thank you twice. See if it'll-
Watching on another. See?
Just have to ask it to do it again once we've got the next data point.
There. There's a copy button.
Yeah, there is, isn't there? And what it hasn't done is it hasn't controlling my computer. Can you adjust the latex code to A4 standard document page size and compatible with overleaf into a new code box? Not doing that. Getting there.
Line.
Probably crash because I think I'm that ticket to the chat. Probably won't. So that's a good verse. Mm. I believe gave the following error with effect in respect to EGF plots.
And 107.
Ali?
We still have a little bit room.
I think we should probably dial it back. We say 348. 348. Nice. I'm going to give AI the benefit of the doubt now and give it 348 and see where it goes.
Yeah.
Not 346. or 350. Oh, it wants to be at 340. Oh, there we go. Oh, come on. Huh? Yeah. Good. You think so? Let's wait for the next 2 second sample. Yeah, looks good. That looks good. Just missing the plot. It's got everything else. I don't think it's using tickets picture. Include a use package for what?
Building a straight line.
Oh, oh, oh. Did it actually get it right? It's going down still, but it's now going up again. I don't know.
It's not as bad as the last times.
Oh my god, it was epically bad because it kept drawing a straight line.
Yeah.
So obviously, if every single one is going down, like it's obviously a radiative thing. I'm saying, and
You didn't complain enough, maybe.
yes, I told you this didn't work because you didn't include use tickets package. Honestly, I have to tell it what to do the whole time. Come with that, guys. Still, still no. Oh dear. Still no trouble. Freedom one. Infinite glue shrinkage found in the paragraph. What does that mean? Infinite glue shrinkage. Same thing. Overly complained with the phrase infinite glue shrinkage used in paragraph. Found in paragraph.
Maybe we should have used HTML or something.
I don't know. Well, maybe. Okay, all right, fine. Let's see if that works. No. They now complain that saying that the control code is not allowed in LR mode. So close. So,
Getting a little bit low.
are we?
2 degrees.
Was AI wrong again?
Just a bit, but it looks good.
Well, yeah, it's flattening out there. That's true.
Never changed to option.
It's pretty close for AI. It's pretty close compared to previous data points.
It's 1 or 2 degrees. Oh,
Yeah. Now it's
okay,
going
so
out,
maybe it's just
settling out.
Mm.
We're on 349 kilowatts. 348 has gone back down to 348 watts. So still trending upwards. But this is pretty darn close. So the moral of the story is what we knew already. Don't try and do a linear fit between 4 data points when you're doing something that's got thermal losses involved. It's very close. That's sort of real. That is definitely way too good for government work. I think around 350 would do it, wouldn't it? Because it's kind of skipping, floating around 348, 349,
Mhm.
and that's coming back down again. Well, let's see if we can get it to go to 350. It's too much, so 350 gives still too much. It's either sensitive or not sensitive at this point. 350? Is it going to stay at 350? 350. Just gave it a stroke on one side towards me. I didn't try and rotate it. I just stroked it on this side. Right. Right, it's still not doing this. The is giving undefined control sequence error.
$900.
Can reach 900.
Yep.
Still going up. Very close.
What do I do? I've seen it already. No.
There we go. It's pretty flat.
Yep.
Over there. Still trending up. Now it's trending down. You see how much easier it is when the AI listens. Doesn't try and do its own thing.
Yep.
900. Still trending up.
Oh,
It's mostly 899, isn't it?
yeah, so
So we have a very flat data over here, which is good. And down here, it's looking very flat too. It's trending up, but it still won't go to 900 where it has done, but now it's trending down. I think I might call that. Now it's trending up. Oh, I think I might call it 899. It's going up and down. Trend. Okay. All right. So we have 350 watts. It was wrong, but it wasn't as wrong as before. For active internal to be 899. And that's gone to 900 there. Just typical, right? Oh dear. The control internal is 870. And Dwyer is 582.8. And the control is 592. It's failing to produce the right latex for this. Something very small. It even added the predicted point for 900.
Yeah.
Okay, we have the data for the last watt temperature, and it is 350 watts produced 899 degrees centigrade. Please adjust the thermally based polynomial for an accurate assessment of watts to temperature at any point. So that's one for checking. Get the context window, that's good for the conversation. And that's polynomial, which is P is approximately equal to 1.762 plus 0.2489 times T plus 1.9 times 10 to the minus 10 times T to the 4. Updated prediction for 900 degrees C is 350.5. Should we see it? Should we add another half? We can't, can we? But it's saying to hit, it's basically unstable. No, to hit 900 stably, it's saying we need an extra half a watt, which is pretty impressive, actually. Yeah. And it's done the updated late in there.
Yeah.
But it
Hasn't
doesn't
worked yet.
It hasn't actually.
Display HTML directly?
I don't know. Let's see. This is not going to work anything.
Okay. No,
It's done it.
that's good.
Yeah. Except we've got it the wrong way round. I want power on the bottom and temperature up the side. Can you redo the latex for overlay with power on the bottom x-axis and temperature on the y? There we go. So that's quite good, right? Yeah. Yeah, that's quite good.
Nice.
And now you should know what power you put in,
Yeah.
which you can just dial on there to get a temperature. You can forget about that. Or you control it like that. You have a servo on there and you can dial in the power. You have a power controller.
Yeah, but it stops at 400 temperature.
No,
Would be nice to
no,
see.
it stops at 950.
No, the lower side. Like if I want to go to 2.
Oh, right, yeah. I'll ask it to extend the polynomial to say, well, you want 200, don't you?
Mhm.
So let's extend it down to 1. Okay, all right, fine. All right. Oh, crap, that doesn't work. Jeez. That one didn't work. It's a correct big one. Oh, it did so well before. I was making the same error as it did before. Well, I'll go back. Can you go back to the previous code and adjust it so that it goes down to 100 degrees and up to 1,000 degrees at either end?
Have you added a question?
I don't know. Yeah. I just want to see if it's actually. It did so well, and then it just got it wrong. There we go. The answer is yes, it's done the job. So you need to put in 50. That's approximately what we saw. So about 50. What's that? 2 watts. So just to show people what we've done with Grok and fitting the 6 data points that we have. Yeah, it's not quite showing you 1,000, but we don't really want to go with 1,000 anyway, do we? I don't know if I can show you, but maybe I can show you here. Like, we use Grok to create latex code, and maybe I can show you on here better. There. Now I'm going to make it smaller. You'll be able to see it. It's going to be on the piss, but anyway. So there we go. So we now have a chart where we can look up a temperature we want, and we know how many watts we need to give it. Conversely, this will be something that we can use for calculating potentially excess power at some point. Anyway, you have the formula there, so you can just put it into the formula what temperature you want to achieve. So there we go. Something like about 52, maybe 55 watts, 54 watts. Will achieve 200.
Try something.
Are you going to put the polynomial in? Mm-hmm. Mm-hmm.
Repeat. 51.85.
Yeah, I said about 52.
Yeah, it's 52 here, rounded.
Yeah.
So it just works by making a photo of it and asking for it once.
There we go. Cool. That's a lot of work, but
Yeah.
no one has to do now.
If we don't change anything.
And we don't change anything at all he needs to do is put a servo motor on there and dial in the watts he wants. So dial in the temperature one. I mean, you could probably put this formula in there.
Yeah.
Easy enough. Wow. I mean, that would be a lot of work back in the day.
Mm-hmm.
If you loading those data points into Excel and fiddling around with the polynomials and this is taking into account the Stefan Boltzmann thermal losses, so it's actually a better model and it's actually more accurate. It even agreed that 350 watts was better than its 346 watts that it attempted to predict, and then adjusted it based on the other data set to actually give us something that would really have produced 900 watts. Well,
no, it's fluctuating because
I'm messing around.
Check the model.
Anyway, so the question is, do we want to choose a point on here? Like, I don't know,
not too far.
250 watts. We should have 750 degrees centigrade. So
I can ask. How many watts?
Well, if you put in 250 watts, we should see 750.
250.
Dial it down. Okay, 250 watts. Oh no, it's gone down.
Solving. 100 and 602. About 600, but 602.
What?
250 watts.
250 watts here is 750. So you've got something on there.
Maybe couldn't read exactly.
Oh, yeah. Maybe big echo on it.
750.
It's pretty clear that that would be it. I almost want to, and I will, screen grab that. Can we get it on here? We've got a normal stick or something. And actually put it at the end of the stream. Well, this is what we got. Whilst it's cooling down, if you've got a USB-C memory stick, then we can load it in as an image.
I do have many, but in rooms where people are sleeping.
Okay. And I might be able to go and get mine when you do that.
Then
because it's going to cool down now. So
my office would be.
No, I know where I got mine. How are we doing with that 750 WC? I'm getting there.
Yeah, takes time.
It's not cool down.
But now my AI says the same.
Does it?
Yeah.
It's caught up with my visual.
Want to calculate exactly? To estimate it something first.
Yeah. That one will be a big space there. I've got 1, 2, 3. Press that down. Maybe. And that. What's that? No, well, thank you for it. Well, that one. Really?
Probably.
Okay, let's see. Doesn't stop the video. That's okay. It's working still. Oh. Right, so what? No, we're going to do it this way. So add an image.
Oh.
Um, browse. Oh, hold on, I do need to copy it. You're right. Let's see what you get there now. Where shall I put it? Firstly, where's copy? There we copy.
Yeah, not straight.
And now where?
Up
Okay.
and there. And then.
Let's paste that one.
Yep.
Okay. No, not that one. That one.
Yep.
Okay. So this is our calibration curve that I'm going to scale. And there you have it. So we can turn that on and off. It's rather beautiful, right? So how we did that is in this video, we captured by manually controlling the pulse width modulator here to target roughly 4, 5, 6, 7, 8, and 900 degrees centigrade approximately. And then we finally convinced Grok to pay attention to non-linear interpolations and the thermal loss model, and then asked it to plot the resulting polynomial into a latex compliant code, into a code box, and then I put that into Overleaf and rendered it, and this is what we have. So now in theory we can say if we want a temperature of 750 degrees centigrade in our core, then we need to put in 250 watts. And that's that really.
Well calculated exactly.
Yeah. And if we wanted to treat our nickel diamond pads at 200 degrees, we need 51.5, 52 degrees centigrade, so 52 watts of input power to be able to drive that to 200 degrees centigrade. And that's it, really. Just like that. And now we have that. So you have literally seen in this video the actual calibration and producing a model for us to calculate temperatures and power relations. There you go. So the question is it actually going to cool down at some point in the future to 750 degrees C? Well, at the moment, it's at 796 and dropping. So it's looking good so far.
But it can take time because we do not undershoot.
No, this is going to cool down, and it's going to cool down, and we're giving it all the power it needs to maintain it when it finally gets there.
Maybe 1.5 hours probably.
Yeah,
Like cooling down completely.
yeah, you're probably right. It is flattening off here, but we convert guesswork into science this way.
Well, we could undershoot.
We could deliberately undershoot and then warm it up.
Yeah.
Let's do that. So we are currently at 251. Let's undershoot by doing this. Don't even care how much I'm undershooting. There you go, 80 watts. Being really Scroogey with power. And we're undershooting. Let's do it properly. We're undershooting right now. There's a lot of undershoot. Let's go down to 700 for the undershoot, or 730.
But then we will have to wait again.
Well, I don't think it's as long as we would have had to have waited. Right, go to 250 now.
Yeah, but you're right. There's so much heat still there.
It's like it's starting to stop the drop, if you know what I mean. No, it's still dropping a bit. No, it's going up again. Problem is, there's so much thermal storage in that thing, it's going to overshoot the other way.
Yeah.
Flattening off, though. As it's doing. Flattening off there. Mate, I think that's a good job. Yeah.
For up to
Just got so much thermal mass there to dissipate. Yeah. Could you eject that memory stick? Please? No. Eject it first.
I've never done this in the last several years.
I've done it because I've lost several.
Yeah?
Yeah. That one. Several memory sticks, and I can't. No. This damn jacket always gives me a lot of static. What else I pulled out? Still working? Still working? Morning, chaps. This morning, Yoni 6177.
Morning.
Happy Easter, yes. Still to those that are on the day, as we are, on the tail end of it. So what we did in this run was we swapped the fritzed thermocouples, which had died because we established later that they can't survive over 800 degrees for very long, and certainly not over 1,000 degrees for long at all with the steel ones. So we swapped those for new ones, and we decided to control the power with the PWM here and do controlled calibration of the internal temperatures and what that means for the monitoring and control temperatures here. And we got 6 data points, and then we put them into so you can see these 6 data points here, maybe with a 12-hour period here. So 1, 2, 3, 4, 5, 6. Okay, this is just us getting up to the rough temperature there. So we have 6 points, 1, 2, 3, 4, 5, 6. And we finally convinced Grok to accept polynomial thermal curve rather than a straight line. And we asked it to produce a calibration curve and give us the code back that could be put into we should put this into Overleaf to render a latex PDF document, and we produce this curve. So in theory, we can put in roughly 52 watts and achieve the 200 watts we need to do the baking to produce the fuel, which hopefully over the next couple of months Artifact here will have time to do, so that I come back and we can actually do an active run, and we might be able to get some ceramic thermocouples, possibly to make it more robust, because those can run to 1100, 1200, no problem without falling apart. And you can see we can run up to 950 degrees on this chart. We know how much power we need to put in. And this can also form a chart like this, a chart that is actually telling you how much power may or may not be generated if there is excess heat. So you can reverse, if the internal temperature is, or we actually need to do one for the control temperatures. Actually, not this one. This one can't predict. We need to look at the secondary temperatures. So anyway, what we're doing right now is we've chosen 250 watts here And we should see, ultimately, after everything's settled down, 750 watts. Sorry, 750 degrees centigrade. I'm getting tired now.
Let's go now.
So there we are. Yeah.
Looking good.
So yeah, so you can see it's going down. It's on the trend down slowly. So perhaps our chart here, 250 watts, gives us 750 degrees centigrade in the so-called active internal. This one, I'll change the chart width here to 1 hour. Yeah, this active internal here is trending down, you can see at the moment. And you can see over here on the power monitor, we got something like 249, 250 watts going in. And so this becomes a fairly predictable thing. Yep, see it's still trending down. Just take time because there's the whole thermal mass of this thing, which needs to cool down when it's been up at a higher temperature. So yeah, in a few minutes we will conclude the experiments for this weekend. Thank you very much for all those that jumped in and said hello. We've learned a hell of a lot about what this can and cannot do. A couple of modifications need to be made, and with the fuel produced, we'll be ready in a future month to do an actual active run. I want to thank my friend and colleague here, Artifact, for hosting this experiment, for buying many of the parts, and for working with me to get this out the door. It's been a long time coming. Of course, Neil Creighton-Gould, the progenitor of this experiment, has passed on, and the person that even made this device here and supplied these parts and many of the things that are being used to perform this attempted replication, Alan Smith, has also passed on. It's a great show. Good friend, both of them. Time waits for no man. Just got to get on with the work. Yeah. So we're still dropping it to 759, 757. And what we are looking to see is, do we get close to this calibration? Shrink that down a bit, maybe. Not to be so big. 750 at 250. 250 in here. And approaching 750 here. That's pretty good from this point of view here, from a quick look see, but it's still a bit high, but it is dropping. It's still going down. You can see it's going down because of this green arrow pointing down. It's trending down. And it's going to get harder and harder to achieve 750 as it gets closer.
Yeah.
It really is very, very powerful, the combination of good data, known science, and being able to ask AI in form of grok, is what I did here, to produce the code in LaTeX to plot a chart. This enables me through voice and the key data points to produce a calibration curve that would have been, it would have involved messing around in Excel and probably making lots of hashes of it in the past. Yeah.
Still going down.
Yeah.
Yeah. And this also.
Yeah, it's great. It's great. Very, very impressed. It's a slow creep, but it's getting there. 7:56. It's going to tease us, right? Well, it was a bit of a disappointment when we saw the fuel cells that were not being prepared. But honestly, even if they had been prepared, we wouldn't have been ready now to be able to run it. And it needs minimum 24 hours, more like 2 to 3 days to do a proper full run. And that didn't mean we didn't have a lot to do. So
Careful baking. It's not
careful baking, yeah, we learned about that. Well, a lot of the problem there was we didn't realize how far off the temperatures were.
Yeah.
And now we know from this plot that when we were trying to achieve 200 watts, in fact, 200, when we got an internal temperature, the Dwyer temperature is at 200, the actual active internal is at 416 or 425 degrees. So we're trying to bake it at 200 and we're actually doing 420. So this makes this a lot more predictable by having this chart. Yes, to bake, we need 52 watts. And the experiment protocol is requesting that you go up to, say, 500 initially, but slowly. And now we know how to achieve that. And then to cycle between 500 and 800 or 500 and 900 or 600 and 900, something like that. And we now know the power input we need to achieve those temperatures in full. Now, it will change slightly when we have something that's more akin to the actual cells, but predominantly it's driven by the thermal losses on the outside and the core heater temperature. So it should be not too far removed from this in an actual run. 7:55 and still dropping. Can we see this out before the end of the day with a perfect hit on the calibration curve? 250 watts is predicting 750 degrees centigrade. 250 watts, and the current temperature is here, 755, 754.8, and still dropping. We have a hint that we're going to hit there because if you look at our proxy for stability, this so-called hotspot, this is indicating a flattening of the curve. Yeah, it's coming down here and then it's flattening off. It's a different part of the reactor. It's actually a different temperature, but the point is it's giving us a proxy for when thermal stability is achieved. That is to say, the input energy is being matched by the loss of energy so that it reaches a stable flat line.
and 53.
Yes. Just going to be hard to get that last little bit, isn't it? Yeah. If you wind back in the video, you can hear me with the exact requests I made of Grok to develop the calibration chart that we have here. Is it going to do it? 7:53.
52.
Wow. How cool is this? It's actually working. It's actually predictable. Whole calibration, uncut, unedited on YouTube. Very nice indeed. Like it. 7:52. There we go. 7:52.5. Really flattening out. Dead flat now. Still dropping. When I say dropping, for those that have just seen, this is a little arrow here. It shows that the trend is going down. This is the active internal.
One.
Similar curves can be produced for all of the different parts. Thermocouples. It is actually the control and the Dwyer that are going to be the ones that we use to choose to set a power level and an expected active internal temperature. Yeah, this is shockingly flat now. And it is only a proxy because it's it's not actually the thing where we're looking. Still dropping at 7:52.1. 7:51. 7:50.6.
First touch.
Wow. Wow, that's really good. Really good.
Really going up.
Yeah.
Should be where it wants to go soon.
That's so close, isn't it? 750.777, 750.625, 750.358,
It will be
750.317.
low because it fluctuates.
Yeah, well, it will go above and below when it gets there, partly because we're actually somewhere between 249 and 250, actually, in terms of the watts. And also because it is actually doing PWM. And sometimes it's on and sometimes it's off. Oh, there we go. Almost 750 dead. Just went under, and what we'll probably find is it goes under and it'll maybe undershoots a little bit, and then it'll be going trending back up, and then it'll be trending back down, and it'll be trending back. Anyway, as we showed earlier, we did 6 steps. You can pretty much see on the 6 hour here. 1, 2, 3, 4, 5, 6. To try and get them flatlining at a temperature around about the first one was around about 400. It was actually 416. Then 500 at 518. Around 600, 619. Around 700, 712. And then because the thermocouple start to degrade from above 800, the next one was 797. And then the last one was 899. And so we use these data sets with Grok to produce this calibration curve. And we're just confirming that with 250 watts in, we can achieve approximately 750 degrees centigrade in the core active. And what we are actually seeing here is exactly that. Exactly that right here. Very, very satisfying piece of work. And your tool here for visualizing the temperatures. Very nice. Thank you, Artifact. We've learned some things that it might need to have to improve it, which is also good to know. Sometimes you have to use these things in anger. Yeah. Oh, this is just wonderful. Look at that. Really stabilizing around that 750 degrees, which is what you want. Look at that. Very nice. So I think with that, we will conclude this of the last calibrations, which should lead for stable control of experiments. So from myself, I'll say buenas noches, dobranoc, good night.
Gute Nacht.
Good night as well. Very good.